Welcome back. In the last video we already took care of the gradient descent method or its basic principles. And in the video before that we already talked about the linear regression model, how it's built, how we use it to generate model predictions. And yeah, now we want to close this up by taking a look at really how to apply it and how we will do it with real data, even though we use simulated data in the example. And we also want to ask a question not only how we evaluate the predictions of the linear regression model, but also once we estimated our model parameters, what can we do with them, how can we make use of them in order to identify like the relationships in the data and find out what are important variables and so on. Okay, so really quickly, just like to really that you understand this here, for the linear regression model, we do not really need the gradient descent method in order to estimate it, because the estimation problem, so the minimization of the mean, the average mean squared error, or like it's not the average, it's the mean squared error, is can be solved analytically, so by a solution. But we just discussed this to prepare you for the later models, because they are in need not directly of gradient descent, but they are in need of numerical methods when we want to calibrate the model. Okay, but for the linear regression model, this is basically the same example that we have seen in the previous video. You can read this on your own or think about this on your own. Just make sure to become familiar with the vector notation here. Always be aware of it when we have the bold letters here, then these are vectors. And also make sure that you understand what is meant by a gradient. The gradient here includes the partial derivatives of the loss function, which with respect to each initial parameter of the model. So you can see this is given here. So really just make sure that you understand this, but not for the linear regression model, but for later models. And then we skip the explanations here of the gradient descent method. Just also here one last note, the mean squared error that we use for regression models is a convex function. Make sure you know what a convex function is. And if you are aware of it, if you know what it is, then it will make sense to you, hopefully, because it will make sense to you that using a convex function, even if you would use a numerical optimization method like gradient descent, kind of is an assurance that we will reach at least the approximate optimal solution of the minimization problem, at least for the data that we use to estimate and calibrate the model. And also make sure that you understand the notation provided here, that we can also write this down if we have more observations than a single observation, and then we can also write this down in matrix notation. Okay, and we will talk about this later anyway, when we can reach more sophisticated models, or when we reach neural networks. So now, before we want to dig into an example which shows you the practical application, how you will estimate a linear regression model in practice using a prepared package in Python, let's first ask the question: assume we have now a multiple regression model with already estimated parameters. So you can see this is indicated by the hat symbol here. But what can we do with this? Of course, we can now use this equation here in order to generate good calibrated predictions for the observations of the target variables. But also, if this works well, we can draw conclusions regarding the importance of the feature variables. So which of the variables drives the result for the prediction the most? And if the prediction is good, then obviously it also helps us to answer the question, which of the variables is most important for the actual real target variable. Okay, and now we just need to switch positions and take a different point of view. But again, we can use partial derivatives, or the information of partial derivatives, in order to derive this information. And so before, and do not mix this up in your head, before with the gradient descent explanations, we were interested in the partial derivatives of the loss function with respect to model parameters. And so this, in our mind, we had like there are fixed numbers, the fixed number in the data. So the feature variables, they are the realizations, are all fixed values. The target variables realizations, they are all fixed values. And the variables, so the function, the loss function, depending on variables, depends on the parameters. Now, assume we estimated the parameters. So now we think of like them, they are fixed numbers at this stage here. And of course, the realizations and the x values are also fixed numbers. But with this prediction function, this is a function, we can obviously generate here partial derivatives with respect to the feature variables. So now we assume that there is not a concrete realization here. We assume that there is like this feature variable, and maybe we can think about of, even if we set a value here, then it's like an example or something. But we ask the question, to which degree changes the prediction for the target variable if the feature variable would change by a small amount. So this again can be done by the partial derivative. Okay, so if we are interested, for instance, in the first feature variable, and we make this for this equation here, the partial derivative of y hat with respect to x1 is simply the parameter estimate here, so theta 1. And the amount here tells us, like, if x would increase marginally, then what would happen with our prediction. So a big number here is usually what people in statistics talk about, a big effect size. So the effect of the feature variable is big if the parameter estimate is big. Of course, just to make sure, only when we want to compare this, then the feature variables themselves all need to be on very comparable scales. So they should be pre-processed before that. They should be brought to the same numerical range, right, in order that we can compare them. But if this is done, then the value here directly tells us if a marginal change in this feature variable would drastically or would not drastically change our prediction. And if it drastically changes our prediction, then obviously the variable is quite important for our predictions. And if our predictions are quite good, which we try to make sure of in the step before when we estimate the models, then a big number here indicates that the variable is quite important for the target variable, okay? And if we just do this for a single observation, so this is given by I here, then this is what we would say is kind of a local, we regard this from a local perspective. Local because locally only at this data point. So if we want to grasp or if we want to derive like the average feature size, the average feature importance of this feature variable, then we want to calculate all the local sensitivities here, which are here, by the way, for the linear regression model, it's all the same. For each observation, it's all the same value. But then we will do this later where this is not the case. So this is why we want to do this from a general perspective here. So locally, we derive for each prediction how sensitive is the prediction to this certain feature variable for this given observation. And this is, in this case, just the value of the parameter estimate for the corresponding feature variable. And if you want to take a look at how this sensitivity, how big this sensitivity is on average for the whole data set, then we average just these sensitivities here, okay? And as we have the same value here for each data point, then it's just m times this. And if we average it, then we have 1 divided times m times m. So again, we end up with the effect size of this feature variable. Okay, we will try to make this really more clear with an example later. But the basic idea here is, again, using partial derivatives, because partial derivatives indicate the sensitivity. And here we are interested in the sensitivity of the target variable with respect to a change in a certain feature variable. And this is how we derive the importance of feature variables. Okay, this is, you should really focus on the idea here, not on the mathematical notation, because this will change, especially when we come to more advanced models, but the basic idea will stay the same. Okay, and as I said before, we need to make sure, but this is something that is usually done, especially in data science, most of the times, that the feature variables are all in comparable numerical ranges, and this is usually controlled by pre-processing them. So the raw data is taken and then pre-processed in a way that they are on comparable numerical ranges. We will talk about this later when we talk about data pre-processing. Okay, so this would now bring us to the next model, which we will not do in this video, but now we want to take a look at the linear regression model example, which you can find in the Google Collaboratory folder. And this is, as I said before, with simulated data, which makes it easier for us because we can set the true effect sizes here. Okay, so here we will give us some parameter values. We will generate 1,000 observations, and we will say, okay, the impact of the first feature will be positive, the second one will be negative, and the third one will be positive. And speaking with absolute magnitude, the third feature will be the most important in our understanding because it has the biggest effect size, and by this means is the predictions as well as the actual targetizations depend the most on the third feature variable. But that's why we're simulating the data here, because we can control it. And of course, always be welcome to alter these values and play around by yourself. You can do this just by copying this file to your folder, and then you can play around with the data as you want to. We also set an intercept here, and now we generate random realizations of feature variables here. They are all in the same scale, so we do not need to worry about that for the simulated example. And here now we generate the actual realizations of the target variable following the regression, the linear regression model, which also includes here the epsilon values, so the degree of randomness in the data. And I mean, for you, it would really be a good idea to, every time you take a look at the examples here, then you will open this in your folder and then go through it line by line, especially in the beginning. So here in the first rows, you see there are only definitions, so nothing's really calculated here. It's just defined. But then, so we need to copy this and we need to start this. This will take a second. But then you can see here that something is happening here, something with function values. So x is generated, something you maybe do not know. So you maybe do not know what does np.random.normal here, okay? So, and always you want to find out about this, just copy this part first and then insert it here. And then you will see what actually, you always see the output that you see here is always what is done here in the last row, or the last line of code. And here, for instance, you can see, okay, maybe this is just something which generates an array with 3 columns and some rows. And if you want to find out what this function does here, then you can, as suggested, somewhere else in the explanations or in the introductory, you can use the help function and copy just the function name, without the brackets, and it also will, give you the information here what is done here. So, for instance, draw random samples from a normal Gaussian distribution and so on. Okay, but I would recommend you to do this on your own, especially if you want to become familiar with Python and how we're working here. And it always holds true, at least for me and all the other people I know. Once you are able to simulate data following a certain model definition, then you really understood how the model works. Okay. So, but what we do here is we generate 3 feature variables and the target variable, and corresponding or according to the linear regression model with some parameters values that are given by us. Okay, now here's some information. You can take a look at that for yourself, but and also some other, like how you get information about the data types, and so on and so on. So this is, you can find out by yourself. But what I want to show you is, for instance, here we get already a visual impression. So where we find probably the most relation or the strongest relation between x3 and the target variable. And we can also see that here it seems to be some negative relationship between x2 and the target variable. But I want to show you actually is, first of all, how you can, how easily you can estimate the model. Sorry, and this is done here at this step by the linear regression function. It comes from the sklearn package, which is, I think, defined here in the beginning. So here you can see it is taken from the sklearn package and from its submodule, which is the linear model module. Always, if you want to find more about this, just Google it. So Google here sklearn linear model, and then usually the first hit will bring you right to very informative documentations of the package. And if you want to really find out about the linear regression model, which you can see here, you can also further Google its name here. And typically this brings you to the documentation of the specific function. And here you really need to become familiar with the explanations. They are really helpful and also accompanied with very short but insightful examples, and so on and so on. So this is just some tips for you. Okay, but so here we have data, we have feature variables, we have a target variable, we already have the model. So let's just copy this and I will show you. So if you really want to estimate the model in Python using this function, you can see here we have here the matrix of the, okay, sorry, we need to first okay, now we're good to go. Here at this place we have the data matrix of the feature variables. We have the vector with target variables, okay, as you can see here. And the only thing that we need to do is we need to define a linear regression model. We could separate this step, so we could first of all just define it, okay, so linear regression. Here nothing happens, just it is defined with this name. So we defined a linear regression model that is called linreg model. And if we want to estimate it, then we can call its internal method the fit function, and it needs the, as you can see here, the matrix with the feature variables as well as the target variable, and then we can fit it. Okay, and once we did this, then there is some information given with this object. You can find which information, taking a look at the attributes here, so it's the coefficients, and here is the explanation what they are, and some other, and the intercept. So we are typically interested in the coefficients. So if we want to find out what are the estimated coefficients, we need to use the object name dot and then the attributes name. And here you can see the estimated coefficients, which are quite close to the ones that we find above. The deviations are here due to randomness when sampling the data. And we can also take a look at the intercept here, okay, which is very close to 1. And now if we want to take at the importance, I mean, for the linear regression model, we could directly just take a look at the coefficients, okay, and here we see, okay, as the feature variables are all in comparable scales, then obviously this is the most important one with a positive impact. This one is the least important one, but it has a negative impact. And if we want to normalize this, we can also use here the sum to normalize it. So the sum over the absolute values of the coefficients here. This would tell us that in percentages. So approximately, like the importance is given here about with 53% for the third variable, 33% of the first feature variable, and only approximately 13% of the second feature variable, but this is here with a negative impact, and the other ones have positive impacts. And this is how we can learn about the importance of each feature variable using the linear regression model. And what I also want to take you as an important lesson here is how easy it is for you to really take data and estimate the linear regression model. Okay, so I will delete this, and I want to encourage you to copy this code and play around with it by yourself, because always everything you do with your own hands, you will understand it way more easier and faster than just taking a look at these videos here. So copy this, play around with it. We will also take a look at an example with real data, and I will give this, of course, you an example of real data in the collaboratory file, which we take a look later. But you're also encouraged to Google, for instance, regression model as sklearn package, and maybe you'll find also some interesting examples by yourself. Okay, so always hands-on, try to play around with it, because in my experiences, this helps you really in quickly understanding what you are actually doing here. Okay, now we're at the end of this video, and in the next video we want to approach to maybe more realistic examples and also to other methods. Take care and see you in the next video. Bye bye.